In parts 1 and 2 of my video presentations investigating thermodynamic non-idealities in CO2 capture with CAF 20, I examined mixtures of CO2 and water adsorption in CAF 20. I demonstrated the existence of two scenarios that manifest at low and high humidities. At low values of relative humidities, the mixture adsorption strongly favors CO2, and at relatively high values of relative humidities, the mixture adsorption favors water, and CO2 adsorption is suppressed. Let's examine adsorption of mixtures of nitrogen and water in CAF 20. We conducted configurational biased Monte Carlo simulations for binary mixtures of nitrogen and water at a total fugacity of 100 kilopascals with varying compositions of water in the bulk gaseous phase. I plot here the component loadings for water, blue triangles, and nitrogen, red circles, as a function of the percentage relative humidity. We note again, just as in the case of CO2 water adsorption, the configurational biased Monte Carlo simulation data shows significant deviations from the predictions of the ideal adsorbed solution theory. We can identify two scenarios that manifest respectively at low values of relative humidity and higher values of relative humidity. Below about 15% relative humidity, the mixture adsorption strongly is in favor of nitrogen and in disfavor of water. However, as the percentage relative humidity exceeds 15%, the adsorb phase is significantly poorer in nitrogen than anticipated by the IAST. The reasons for the deviations from IAST expectations is precisely analogous to those discussed earlier for mixtures of CO2 and water adsorption. The message to emerge from the molecular simulations is that thermodynamic non-idealities are not just restricted to mixtures of CO2 and water, but also nitrogen and water. Let's turn our attention to the adsorption of mixtures of carbon dioxide and nitrogen in CAF 20. The experimental data of Nguyen and Rajendran, published in Chemical Engineering Journal in 2022, are shown here, and the experimental data for mixture adsorption shown by the red squares for CO2, black squares for nitrogen. The nitrogen scale is on the right axis, the CO2 scale is on the left y-axis, and the experiments were carried out at a total pressure of 97 kilopascals and a temperature of 295 degree Kelvin. The IAST estimates of CO2 loading and nitrogen loading are shown by the blue crosses. We note here that there is a slight deviation between the IAST estimations for nitrogen loadings as compared to the experimental values. Now, in order to understand these small deviations from ideality that were reported in the experiments by Nguyen and Rajendran, we carried out molecular simulations for adsorption of mixture of CO2 and nitrogen at a total pressure of 100 kilopascal at a temperature of 298 Kelvin. On the x-axis, we have the variation of mole fraction of CO2 in the bulk gas mixture. The red circles are the CO2 loadings from molecular simulations. The blue triangles are the nitrogen loadings in the adsorb phase, and the axis for the nitrogen loading is on the right-hand side. The dashed lines are the estimates of the IAST. What we observe is that the IAST is in excellent agreement with the CBMC simulations for mixture adsorption of CO2 and nitrogen. And therefore, these small deviations observed in the experiments of Nguyen and Rajendran are perhaps due to the fact that the experimental data that is reported and presented here are based on breakthrough experiments that are not conducted under precise isothermal conditions. In order to further verify that the IAST predictions for CO2 nitrogen adsorption are in good agreement with the data from molecular simulations, we carried out another set of molecular simulations in which the composition of the bulk gas mixture is maintained at 5% CO2, and the total fugacity of the bulk gas phase mixture is varied from 0 to 100 kilopascals. Again, we see that the IAST provides excellent estimates of both CO2 loadings and nitrogen loadings. The details of the molecular simulations are provided in my paper published in Separation and Purification Technology 2024.